Okay, now what we want, so we looked at the geometric series, and we know with a geometric series for sure how to tell if it converges or not. And if it converges, we can find what it converges to. But I want to talk a little bit about what we mean when we say something is converging. Like, for example, let's suppose that we've got this series right here. Let's suppose we've got -1 to the n, and n goes from 0 to infinity. And what we want to know, does that series converge? Well, look, if you expand this out, you put in a 0, you get 1, minus 1, right? That'd be the next term. Plus 1, that'd be the next term. Minus 1. And it just keeps oscillating back and forth, right? You know, and it goes on forever. Now, if you look at that, you might be tempted to say, well, the sum is going to be 0. Because every one it zeroes out because the next term is a negative. So you could say this is 0, this is 0, this is 0, and on and on. And you would say, yeah, that converges to 0. But no. What we have to do is we have to come up with something that we can agree upon, that when we say something converges, here's what it means. And the fact is, this thing oscillates, but I mean, if you look at it, it goes 1, then -1, 0, 1, then -1. So we're not going to say something like this converges, even though you might be tempted to. What we're going to do is we're going to define convergence by something called a partial sum, or partial sums. Now, let me show you what a partial sum is. If we have, let me just make it simple. Let's suppose I have k squared, like that. And we want k to go from 1 to infinity, let's say, or yeah, 1 to infinity. Okay. If we have something like that, we can talk about partial sums. Now, partial sum will denote this way. So this is a partial sum. A partial sum goes like this. We say the first partial sum, we'll denote it S with a little subscript. And that's just when you look at the first term. The first partial sum is 1. And the fact is, whenever we limit this, whenever we're not going to infinity, we've got a partial sum. So we could say this. We could say, okay, what about the second partial sum? Well, that's the first partial sum plus the next term, right? The next term, which is a 2 squared. So we get, 1 plus 2 squared. That's the second partial sum. Now, so just to be clear, if we're talking about just like the fifth partial sum, for example, we might say this. The fifth partial sum is equal to this. K equals 1 to 5 of k squared. That's the fifth partial sum. Now, what we're going to do is we're going to say this, that if the nth partial sum converges, and if the limit of the nth partial sum converges, that's what we're going to call convergence. In other words, now let me illustrate. If you look at these partial sums, if you look at S1, S2, S3, and so forth, this is a sequence, right? These are just terms of a sequence. Now, what we're going to say is, if you take the kth sequence, in other words, if you think of a formula for this, this, and this, if you think of a general formula for the kth partial sum, and you've got now a formula for a sequence, if the limit of that exists, we say, okay, well, that is what it converges to. Okay? So we're looking for the limit of the kth partial sum. Now let me illustrate what I'm talking about. Let's suppose that we have this thing. And k goes from, let's say, 1, or actually we could just say 0 to infinity, right? And let's suppose I want to determine if that converges or not, or let's just say I want to know what it converges to. Well, I want to look at the partial sums. So here's what I'm going to do. And let me go ahead and let me just start this at 1. Okay. So I just want to find the first partial sum. Okay. So this particular problem is we're going to call this a telescoping series. And you'll see why as we go along. But here's what I'm going to do. This is the second type of series that we can actually find what the convergence is. So I'm going to take this right here and factor it. Okay? So there's nothing wrong with just factoring the denominator. And also, you can take those with you. And also what I want to do, I want to use partial fraction decomposition to, and you'll see why I want to do this. So I'm going to use partial fraction decomposition because what I want to do, I want to try to find a pattern in the partial sum, in the sequence of partial sums, so that I can come up with a formula for the nth partial sum. That's what I want to find out. So I've got this right here, and now I'm going to write this. We know how to decompose using partial sums. And I tell you what, for simplicity, let's change this 1 up here to a 2, okay? Just change that to a 2. Yeah. Yeah, because that's going to make these numbers come out better, I think. Okay? So let's just make this 2 over 4k squared minus 1 and so forth. Okay. Now, if I do that, what I can do at this point is I can find my a and b, right? So I've got, let's just do this. Let's let k equal negative 1/2. And if k equals negative 1/2, look what I have. I have 2 equals, now this part right here just goes to 0. But this over here is negative 2b, right? This one is negative 2b, right? Because we got negative 1/2 times 2, that's negative 1 minus 1, negative 2b. And that gives me that b is equal to negative 1. Does that resonate with you? That's my new thing instead of do you dig it? Does it resonate?
You're changing it up.
I'm just adding things, right? Is this resonating? Okay, then we can do this. We can say, well, what about if k equals 1/2? Well, if k equals 1/2, then we get, going through the same process, we get 2 equals 2a, and that means a equals 1. Now we have a partial fraction decomposition. You might think, well, that was just, why did we even do that? We're not trying to integrate this. Well, look, let's put this together now. We have this summation. K goes from 1 to infinity, 1 over 4k squared minus 1, well, 2 over, right? And what was A? A is 2. A is 1. So k goes from 1 to infinity. What was this down here, 2k minus 1 or plus 1? What was on the bottom of A? 2 minus, okay. And then we had minus 1 over 2k plus 1. Okay, now, the reason we do this is just so that you understand what we mean by partial sum and what we mean by when we talk about the limit of the nth partial sum. So here's a partial sum. Here's the sequence, the series that has just been rewritten. And you'll see why I rewrote it, because now I'm going to find the first partial sum. The first partial sum is just going to be 1 over 1 minus 1 over 3. Is that right? Did y'all see that? All I did was I put a 1 in place of k, and I got this. 1 minus 1/3. Is everybody okay with that? That's my first partial sum. Now, I'm going to find the second partial sum because I'm looking for a pattern. So right now, I don't really see any pattern. But I do the second partial sum. Now the second partial sum is going to be the first partial sum, and then me putting in 2 for k. So this is going to be 1 over 6 minus 1, right? 4 minus 1, which is 1/3. Do y'all see that? Minus, if I put in a 2 here, I get 1 over 5, right? Does everybody see what I did? This is the second partial sum. Now, let's just see what happens here. Notice that these little fellas here go away. And look what you get. You get 1 minus 1/5. Does everybody see that? Now, I want to take a minute and think about this first partial sum. This first partial sum was when k equals 1. And look what I got. I got 1 minus, can I put it in terms of, what is 3? This is 2k minus 1? This is 2k plus 1, isn't it? Is that what that is? And if k equals 1, then I've got 1 minus 1/3. Yeah. So what about this one? This is 1 minus, is it also 2k plus 1? See, 4 plus 1? Do y'all see that?
Yeah.
Hot dog. It looks like I've got a pattern going here. Now, I want to do one more partial sum, and then we'll see if there's a pattern here. So I'm going to do the third partial sum, which is the first partial sum, the second partial sum, plus when I put in a 3. So if I put in a 3, I get 6 minus 1, that's 1/5. We knew that was coming, didn't we? Sorry about that. Yeah, I got to figure out what causes that. And then what's the next term? 2k plus 1? So that's 1/7? Is that right?
Yeah.
Now look, these ones, they're gone, and I've got 1 minus 1/7. Now that is 1 minus 1 over 2k plus 1, isn't it? When k was equal to 3. So look, now here's the thing. Once we see that pattern, we can say, well, I don't have to do this all day. I see this, that the nth partial sum, what is the nth partial sum? What is it? 1 minus what? 2n plus 1, that's right. There is the nth partial sum. So I could keep generating these partial sums, but it's always going to be that. Now, here's the deal. If this limit exists, if this limit right here exists, then we say, that's what that series converges to. Now, we won't always be able to find this limit. We won't always be able to put together a formula like this. But this illustrates that when we say this, when we say the limit as n goes to infinity of 1 minus, of s of n, what is this limit? Yeah, it's 1, because that's going to be a 0, right?
Yeah.
So that sum adds up to 1. It converges to 1. The fact that this limit exists right here, that tells us that's what we mean. When we say something converges, we mean that the limit of the nth partial sum exists. Okay? Now, so for that reason, we can't say that the sum of -1 to the n converges. It just goes from 0 to 1, 0 to 1, 0 to 1. We're not going to say that converges. Maybe you'd want to argue that's 0. But no, when we talk about converges, this is what we want to do. We want to use this. Does everybody see that?
Yeah.
For the -1 to the n, what if infinity is an odd number? Then it's...
Yeah, you see the problem with it. It wouldn't make sense to talk about that converging. Although intellectually you might think, well, yeah, it's going to be 0. But no, we're dealing with infinity here, right? Okay, now look. Does everybody understand this? Now I want to show you something, one more thing. When we talk about series converging, we're going to get to the point where we won't be able to tell what the series converges to. We are just going to try to find out, does it converge or not? And sometimes that's going to vex us. That's going to be a very vexing problem. So what we want to do is we want to kind of build up an arsenal of tests that we can use to determine if something converges or not. Now the first thing we're going to look at, and I'm just going to throw this in here, is called the Nth Term Test. This is the very first test that we're going to use to determine, to tell us something about whether or not the series converges. But this is not going to be a test to tell us if it converges. It's going to be a test to tell us that it definitely does not. In other words, it's going to be like a screening test. This is always going to be the first test we use when we're given a series. If it doesn't pass the nth term test, then the series diverges. So this is going to be like a screening test. And let me show you how it works. If we have a series, let's just put in here a sub n like this. Now notice that a sub n, this would be a sequence, right? So this is some formula in here. So let me show you. This is maybe 1 over, let's suppose we've got something like that. And I'll say n goes from 1 to infinity. Now notice, if this happens, if this is necessary, the limit of whatever's in here has to be 0. That is necessary for you to have a convergent series. If that doesn't happen, then the series does not converge. So for example, and I'm going to show you why this is the case in a minute. For example, let's suppose we've got n equals 1 to infinity, and we've got 2n squared plus 3 over n squared plus 5. Well, let's look at this one. The limit as n goes to infinity of 2n squared plus 3 over n squared plus 5, that is 2. That's not equal to 0. So this series definitely diverges. So this is a test to tell us if the series diverges. I mean, it's necessary that this limit be 0 to have any hope that the series converges. Now but it's not sufficient. Having that limit be 0 is not sufficient, it's just necessary. Let me show you what I mean. If you have this series, this is a well-known divergent series. This is called the Harmonic Series. And if we do this, if we say the limit as n goes to infinity, 1 over n, that equals 0, yet this series still diverges. So this is not a test to tell you if the series converges. It's a test to tell you if there's any hope of convergence. Because if this limit is 0, okay, you still have to work. If you get this up here, you're done. You say, this series diverges. But if you don't get a 0, if you do get a 0, you have work to do. Well, it apparently doesn't get small fast enough, right? We'll see. Later on, we're going to see why this diverges. But like 1 over n squared converges. 1 over n diverges. 1 over n to the point 1.00001 converges. 1 over n to the 1 doesn't. You can make a slight change, and one converges and one doesn't.
We talked about this before, but I still don't think, why doesn't it? I feel like it would hit it.
Well, we'll explore that. Let me do one more thing. Yes, ma'am.
Can you scroll up to that first example you have right there?
Yeah.
So that one,
This one converges.
the one above that, that's just there, right?
Yeah, this is just there.
Okay.
So in other words, if I've got something in here, what the nth term test tells us is that this absolutely, that has to be 0. And if that's not 0, then your series flat out diverges and you can just go on with your life. Okay. Now, let me show you why that might work. As we go through here, each of these tests, I want to convince you why that's got to be the case. In other words, why does that term of the sequence, the nth term of the sequence, why does it have to be 0? Well, think about this. Let's just think about a finite series. Or let's think about a partial sum, okay? Let's think about a partial sum, and let me make this like the sixth partial sum. Okay, this, this right here is the sixth partial sum. Okay, that's what that is. Now, you realize that the sixth partial sum also could be written as this. It's the fifth partial sum plus a sub 6, right? That's another way to write it. Okay. That means that, okay, so, well, let me do this. So this partial sum, okay, now let's suppose that, well, tell you what, there were two different ways to approach this proof, and I'm gonna go this other way. Let's suppose that we know that the sum of a series is, well, I tell you what, let's do this. Let's suppose that we've got the k minus 1 partial sum. Now, let's suppose that, okay, so this is, that, right? Is that true? Okay, so does everybody agree with that?
Yes.
Okay, now let's suppose that this is a convergent series, right? Let's suppose this is a convergent series. Would you agree with this, that the limit, and let's suppose it converges to something like L or something, but let's suppose that we've got this. The limit as k goes to infinity of s sub k, let's suppose that converges definitely. And let's suppose it converges to L, okay, just L. Would you agree that if s sub k converges as k goes to infinity, then s sub k minus 1 is exactly the same, right? It's just one behind, right? So if I let k go to infinity and that converges to L, then so does this. This also converges to L, right? So really this would be L plus a sub k, right? Does everybody see that? In other words, s sub k minus 1 and s sub k, they're going to have the same limit as k goes to infinity. Definitely, right? So do you agree that this is true then? Okay. Now, what if a sub k, what if this limit right here is not 0? Then the limit of s sub k is not L, it's L plus something else, right? So for this series to converge, for this to have a limit, I mean, for the series to converge, this absolutely must be 0. Because if it's not, then it's not converging. I'm saying it converges to L, but if this right here is not 0, then it's not converging. Are you digging that?
Yeah, I was maybe.
I mean, does it make sense that it has to be the case? Because if it doesn't, then this thing is just getting bigger. Right? It's getting more terms added to it. But so this must be 0. Okay, any questions about that?